Have you ever wondered what powers an electric vehicle? It's not just about batteries, it's the magic of electric motors and motor controllers working together. Introduction. In today's video, we're diving deep into the fascinating world of electric vehicle, EV, motors and motor controllers. You'll learn about different types of motors, how they're controlled, and the basic operating principles that make EVs so incredibly efficient. Whether you're a curious driver or an aspiring engineer, this is your complete beginner's guide to EV motor systems. What are electric motors? Electric motors convert electrical energy into mechanical energy. They are the heart of any EV, providing the torque needed to move the vehicle. Types of motors used in EVs: DC motors, brushed and brushless. Brushed DC motors are simple and cost-effective, but wear out faster due to brushes. Brushless DC, BLDC, motors are more efficient and durable. Analogy. Think of brushed motors like shoes with worn-out soles over time, whereas brushless motors are like shoes with permanent soles. Induction motors, AC motors, popularized by Tesla. These motors are rugged, reliable, and require less maintenance. They operate based on electromagnetic induction without any direct electrical connection to the rotor. Permanent magnet synchronous motors, PMSM, use permanent magnets to create a constant magnetic field. Offer high efficiency and compact size. Switched reluctance motors, SRM, simple construction with no permanent magnets. Known for robustness but can be noisier compared to other motor types. EESM, externally excited synchronous motors, no permanent magnets, magnetic field is generated externally. Emerging as a sustainable alternative for high-performance EVs. Basics of motor controllers. Motor controllers act as the brain that regulates the motor's performance. They control speed, torque, and direction based on the driver's inputs. DC motor control using PWM, pulse width modulation. PWM rapidly switches voltage on and off to control the average power delivered. Example. Like adjusting a faucet to get the perfect water flow. The wider the pulse, the faster the motor spins. Induction motor control based on frequency. Speed is directly proportional to the frequency of the AC supply. Lower the frequency, slower the motor. Increase it, and the motor speeds up. Real-world analogy. Think of frequency like the pace of a dance. Faster beats mean quicker moves. BLDC motor control using Hall sensors and controllers use feedback from sensors to precisely manage motor timing. Ensures smooth and efficient operation, critical for EVs. PMSM and SRM advanced controllers employ field-oriented control, FOC, and advanced algorithms. Allow precise control of torque and speed, enhancing overall driving experience. EESM motor controllers control both stator and rotor magnetic fields independently. Require highly advanced and dynamic control systems, blending efficiency with flexibility. Pro tips or bonus section. Interesting facts. Induction motors have no physical connection between stator and rotor yet can produce incredible torque, almost like magic. BLDC motors are used not only in cars but also in drones and e-bikes due to their lightweight and high-efficiency properties. EESM motors are gaining popularity because they eliminate the dependency on rare earth magnets, making EVs more sustainable. Switched reluctance motors, SRMs, can survive extremely harsh conditions where traditional motors might fail. Pro tips. When designing an EV, choosing the right motor controller combination can greatly influence performance, range, and cost. Always remember, higher motor efficiency equals longer vehicle range. Controllers also play a critical role in regenerative braking, where the motor acts as a generator to recharge the battery while slowing down. If you found this video insightful, don't forget to like the video, subscribe to the channel for more educational content, and drop a comment below if you have any questions or want us to cover a specific EV technology topic next. That's a wrap on understanding electric vehicle motors and motor controllers. Next time, we'll dive into how regenerative braking systems work and how they can actually extend your EV's range. Stay tuned and keep exploring the future of transportation with us. Regenerative braking is one of the most innovative features in electric vehicles, EVs, and it plays a major role in improving energy efficiency and extending driving range. Let's break down how it works and why it's so beneficial. What is regenerative braking? Regenerative braking is a process that allows an electric vehicle to recover energy that would otherwise be lost during braking. In traditional vehicles, pressing the brakes converts kinetic energy into heat through friction, wasting it. In EVs, that same braking moment is turned into an opportunity to generate electricity and send it back to the battery. How it works. Step by step, the car slows down when you lift your foot off the accelerator or apply the brakes. The wheels begin to slow. Motor becomes a generator. The electric motor that normally drives the wheels reverses its function. It now acts as a generator. Kinetic energy converts to electrical energy. The kinetic energy of the spinning wheels is transformed into electrical energy through electromagnetic induction. Energy is fed back to the battery. This electricity is stored back into the EV's battery pack, increasing the available driving range. Real-world analogy: think of it like cycling downhill with a dynamo light. As the wheel turns, it powers the light. You're not wasting that motion, you're putting it to good use. Benefits of regenerative braking: extends driving range depending on the terrain and driving style. Regenerative braking can recover up to 10 to 30% of the energy, effectively extending how far you can drive on a single charge. Reduces brake wear: since regenerative braking uses the motor instead of traditional brake pads, the mechanical brake system experiences less wear and tear. Improves efficiency in stop-and-go traffic, ideal for urban environments. More braking means more energy recovered. Customizability: many EVs allow you to adjust the strength of regenerative braking. Light region for highway cruising. Strong region for city driving, sometimes allowing for one-pedal driving, where you rarely need to touch the brake pedal at all. Limitations: region braking becomes less effective when the battery is full, since there's nowhere for the energy to go. It's also less effective at very low speeds, where traditional brakes take over. Troubleshooting motors and controllers. 1. Basic visual inspection. The very first step when troubleshooting motors and controllers is to perform a thorough visual inspection. Check all the wiring for any signs of loose connections, frayed insulation, or burnt spots. Inspect all connectors to ensure there is no corrosion, broken pins, or rust buildup. Burn marks, melted wires, or a burning smell are immediate indicators of electrical issues that must be addressed before further testing. 2. Power supply checks. A faulty or weak power supply can often be the real cause behind motor or controller failures. Start by measuring the voltage at both the controller input and the motor terminals using a multimeter. Ensure the battery is in good condition, because low battery voltage can cause motors to stutter, behave unpredictably, or not run at all. Also, verify that any fuse or circuit breaker installed in the system hasn't blown or tripped. Replace fuses or reset breakers if needed. 3. Controller self-check. Many modern motor controllers come equipped with diagnostic self-check features. Typically, they have LED indicators that either blink in patterns or stay solid to display their health status. Refer to the user manual to understand what different LED signals mean. Some controllers also log error codes, which can be read via displays or programming tools. Decoding these signals gives a clear idea about what the fault might be, helping you quickly isolate the issue. 4. Motor-specific troubleshooting. When the motor itself seems to be the problem, it's important to diagnose carefully. If the motor is not running at all, it could be due to no power supply reaching it, loose connections, or a faulty controller output. If the motor runs but feels weak or underpowered, check for low voltage conditions, overheating problems, or wrong controller settings. If the motor is running with jerky movements or making abnormal noises, it may indicate Hall sensor failures or worn-out bearings. Lastly, if the motor spins in the wrong direction, it usually points to incorrect wiring in the phase sequence, which can be corrected by swapping 2 motor wires. 5. Controller-specific troubleshooting. If you suspect the controller is at fault, specific symptoms can guide your diagnosis. A controller that gives no output to the motor at all might have failed MOSFETs or internal component damage. If the controller is overheating during operation, it could be caused by excessive current draw from the motor or poor heat dissipation. Random shutdowns typically occur due to thermal protection kicking in or current limits being exceeded. Regular monitoring of the controller temperature and checking load conditions will help prevent recurring issues. 6. Advanced tests beyond basic checks. Advanced diagnostic tests help confirm motor and controller health. Use a multimeter to perform a continuity test between motor phase wires. There should be no open or completely shorted connections. Then, measure the resistance between each pair of motor phases. All readings should be approximately equal. For motors with Hall sensors, test the sensors by slowly rotating the motor while monitoring the voltage at each Hall wire. A properly working Hall sensor will toggle between high and low voltage as the motor spins. 7. Common mistakes to avoid. Many failures occur due to common mistakes during setup and testing. Never connect or disconnect motor wires while the controller is powered on. This can cause internal short circuits. Avoid assuming that the controller is faulty without first testing the motor and the power supply independently. Always ensure the motor and controller are compatible. For example, a sensorless controller will not work properly with a motor that requires Hall sensor feedback unless specifically supported. 8. When to replace versus repair. Knowing when to repair and when to replace components is crucial. Replace the controller if you notice a strong burnt smell from inside the casing or if the controller shows no response even after resets or firmware reloads. Replace the motor if you detect internal shorts, physically cracked casings, or significant mechanical damage. However, you can attempt repair if only the connectors, Hall sensors, or bearings are faulty, as these can usually be replaced easily and cost-effectively. Pro tip: always test using known good spare parts whenever possible. Swapping a motor, controller, or power supply with a known working one is one of the fastest ways to identify which component is causing the problem. This method saves a lot of time compared to testing each element individually.